Okay, here we go.
There we go. All right.
Alright,
So MD, can you tell me what to put in my calculator for this problem to get the probability that x is greater than or equal to 13?
so you're gonna do 1 minus, you're gonna do a second farce,
Right.
go down to binom CDF,
CDF, right?
and then you're gonna put in, so it's the number of trials, so that'd be 21,
Right,
and then a comma, and then the probability, which would be 1/3,
right.
and then the,
Yeah, what would be the number you put in?
X value.
yeah, 13, right?
Well, this one is greater than or equal to 13.
So it's 12.
12, right.
12.
Because 12 and below is the complement of 13 and above.
Minus.
So make sure you make that adjustment there.
Hopefully got it right.
All right, so that's how you would put that in, and if you did that, you get a 0.68%. So this is what really happened in the class. So what does that tell us? If the probability is so low, 0.68%, were they really guessing? Were they guessing? Because this is the probability of 13 people guessing correctly. That's very low, probably impossible. So therefore, they weren't guessing. They knew. They had some water skills. All right. All right, we'll finish out today with a very important point. So this will be pointed back to many times in the year. So I don't know what we can say about this moment in our time together. We'll have to mark it some way with some phrase that will bring this day rushing back to us. So let me teach it to you and then we'll see what we can name it. All right. Is this a binomial random variable? We had to do that in our homework. I liked that question. Is this a binomial situation or not? Take a note on it. There are 10,000 CDs. And we're going to take a simple random sample of those. And when we do that, we're going to pick, of those 10,000, we're just going to pick 10. So we're going to take from those 10,000 randomly, we're going to choose 10. It is a known fact that this company, their machines mess up 10% of the time. So they need some repairs done, but they're still producing. So that means that 10%, the probability of x equals a defect is 10%. 10% all of these in the company will be defective. So x is the number that are defective. So I am going to ask, is this the binomial? So start down the bins. So is it a binomial? Is it binary? It is, she says. That's defective or not. All right, what about independence, MK?
Yes.
Why is that?
Because if one CD is defective, it doesn't affect the other ones.
Well, when you're taking them like this, it's sort of like when we were dealing the cards. Remember that situation where we selected 10 cards from a deck, and we wanted to know how many were, I don't know, face cards or hearts or whatever. So it turned out, since the first one, if the first one was a heart, made the second one's probability different. So they're not independent. Usually if it fails independence, it also fails same probability. But the number is selecting was 10, so it almost made the bins, but just for that. So let's talk about this. This is not a true binomial random variable because it fails independence and it fails same probability, just like the cards in the deck. Remember that one that you got? And you kept saying, no, it's not a random variable, and you were right. So let's say if it was. Let's just pretend for a moment. Want to play pretend? All right. Assume it is a binomial random variable. what would be the probability of x equals 0? That's no defects. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 different CDs that we have chosen at random. What's the probability that the first one has no defects in it? MD? I guess if we're saying
0.9.
x is 0, let's, all right, let's say that there's no defects. So the first one would be 0.9 is no defects, right? Because 0.1 is when there is a defect, so 0.9. And then what about the second?
0.9.
Right, so we're going to do 0.9 times itself 10 times. So when I put that in the calculator, it came out to 0.3486. All right, but that's making an assumption that is not true. So now let's do it for real, or at least start down that path. All right, so now we're going to do it as if it is a true probability problem. And so what's the probability of having, writing it out the long way, the probability of it being okay in the first draw is, we're going to draw, how many are, what is the probability of getting the first one that has no defects? So to do that, it would be 9,000, well there's 10,000, and we know 10% are defective, so would it be 9,000 out of 10,000 for the first one, for the first draw? Okay, so that's the first draw. Now it gets crazy because the first one we drew was defective. So now there are not 9,000 left. How many are left?
8,900.
Yeah. All right, so, and how many total are we drawing from now?
9,999.
Yeah, I told you this would be a pain. All right, so, I'll skip you. MK, what is the, so you can rest your voice. Don't rest your brain now. All right, MK, what would be the next probability?
8,998 over 9,998.
90 what?
8.
Okay.
It's the
All
same
right.
thing on the top and bottom except 8.
That's true. So with that in mind, can you imagine that we did all the ones? So this is the first, second, third. So we're doing 4th, 5th, 6th, 7th, 8th, 9th in the dot, dot, dots. All right, and what would be the last one then? Can you imagine that, MD?
No.
Well,
Do
this
it.
went 0, 9, 8.
7.
So
6.
7.
Do it on your fingers.
7, 6, 5.
Minus 10, dude.
What?
Right.
I'm not good with that kind of stuff because then there's always like,
One
if it's
off.
10, is
Yeah,
it like
I know. I ended up doing my fingers too. All right, so what about the bottom number?
9,991.
All right. All right. Well, somebody did that and did the whole thing and tapped it all out,
Isn't that
and they got ta-da, 0.3485. So look at that.
That's the same.
Look how close it is. This is tenths column, hundredths, thousand, 10,000ths column. This is 1/10,000ths different. So could you live with that difference? Which is easy. MD, all right, you get to do it this way. You get to do all your problems this way. And the rest of us who can live
I'll
with
be
it.
here till like 3 o'clock in the afternoon on the test.
I know.
Forget all
We
that
are
nonsense.
going, in situations like this, we are going to assume a binomial random variable when it's not truly one. When I say situations like this, it has to follow this idea. This has to be small compared to this. Do you see why? Because that creates this kind of number progression that doesn't affect the whole probability very much. Even though truly we lose a choice on each factor on the top and the bottom, the numbers are so large it doesn't make very much difference at all. So we are going to assume it's binomial if, and this is the if. And I say when this is large, when the whole population is large and the sample is small. When I say that, how large, how small. So I'll give you a little rule. If, we'll call the total population capital N and the sample population little n for reference. So we'll say if n is, we'll take n, that's the small number, and we'll multiply it by 10. That's going to be the rule. And if that number is still below big N or equal to, we will assume binomial random variables. So we're going to take the sample number, and so 10 times 10 is 100, and that's still way below 10,000. So if that is true, we will say this situation is mimicked enough that we can use this idea and assume I for independence and assume S for the same probability. Is the probability really the same? No, look at how it changes each time. But they're so close that we're not going to care that much, except for MD. All right, now. Your book doesn't say it this way. Here's how your book says it. It says n is less than 1/10 of the population.
Oh, no.
So which one do you prefer?
I don't like fractions.
So, but in your mind, which is clearer? Taking the sample number that's just relatively small and multiplying it by 10 and saying that's less than the large population, or taking the sample and saying it's less than 1/10 of the population? These are saying the same thing.
I like the first one better.
I do too, but I just figured that it was my weird brain because this is how they teach it. But these are identical ideas, so either one works, so use either one. Alright, so this can only happen when the sample is small and the population is large. Now, so when you're doing bins, when you get to here, to the I, if it fails in your mind, you have to check whether this 10% rule works. So then you're going to have to check n 10 times little n, see if it's less than or equal to big N. Alright, so that's a good place to stop. And your assignment then, I should have given you earlier, is read page 390 to 397. You'll be reading this stuff. And we'll do these 4 problems, 79, 82, 83, and 85. Did Brian get that?
Yep.
Okay, Brian, get well. We need you back. So,
Bye, Brian.
bye.